Hi everyone, my name is Tejas Gokhale, and in this video I will give you a teaser about our new paper STRO, which is Semantically Distributed Robust Optimization for Vision and Language Inference. Feel free to pause the video to read the slides carefully. This paper deals with the task of VLI, which is the task of predicting if an input text is true or false for the given input image or video. So in this case, there are two images and a sentence is provided, and the sentence is false for these two images. Similarly, you can do the same task for videos. So given this video and subtitles, this sentence is true. You can also consider VQA, the yes-no subset of VQA, as a VLI task because questions here can have yes and no as the answers, which is true and false. Pre-trained language models, vision and language models, have improved the performance on all of these three test sets, and this slide shows the results of the state of the art. In this work, we started by analyzing if VLI models can understand semantic sentence transformations. So in this example, when the word ferrets is replaced by cattle, VLI models still predict true, which is wrong. When the number 2 is replaced by 0, VLI models refuse to change their prediction. When a negation is applied to the sentence, VLI models make an incorrect prediction. When a noun phrase is replaced by a pronoun, the output should remain the same, but VLI models fail here as well. When the sentence is paraphrased, the output should remain the same, but VLI models fail again. So to analyze this behavior at scale, we created a set of automated text transformations of two types. The first type is semantics inverting transformations, which transform the sentence and invert the label of that sentence. And semantics preserving transformations transform the sentence but keep the same label. So this table shows each category of our transformations. You can pause the video to look at these examples. The results are summarized here. So as you can see, for all three benchmark test sets, performance of VLI models is random, which is close to 50% when tested with SISP transformed examples. This leads us to believe that we can use SISP transformations during model training. Our method is inspired by group DRO, which is a prior approach on robust optimization. You can pause the slides to look at the details of group DRO. In this paper, we assume access to semantic transformations via our SISP method. We can use the output of each transformation as a group G, and the collection of samples that we can generate using SISP is our uncertainty set. Then SDRO proceeds by minimizing the worst case expected risk over these groups, and we can have two variants of SDRO. The first greedy or sample-wise variant, which picks only the loss maximizing transformations, whereas group-wise DRO does pick loss maximizing transformations, but with a uniform distribution over all groups. We can also do test time ensembling. So once the model is trained, we can leverage SISP transformations at test time. So given a sentence, we can obtain multiple views of that sentence, obtain predictions for each of these views, and then average or ensemble these predictions to get the final prediction. That explains the method. Now let's look at our experimental results. These are the three data sets, and these are the four evaluation metrics we'll look at. If you look at the benchmark test set accuracy, on all three benchmarks, SDRO beats the prior state of the art. SDRO plus test time ensembling leads to further improvements, which shows that our method and our transformation method is effective during training and also helps during inference. Evaluation of models on SISP transformed versions of benchmark test sets shows that on all three benchmarks, our method beats prior baselines, and training with SDRO is beneficial for linguistic robustness. We use reliability diagrams to visualize model calibration. The key observation is that SDRO methods have the lowest ECE on both test sets compared to baselines and are closest to ideal calibration. We evaluate baseline models and SDRO on text attack, which are text-based adversarial attacks, which are not seen by the models during training. And again, training with SDRO can make models robust against automated attack recipes. We train models with a smaller subset on the x-axis of the original training set, and the conclusion is that SISP improves performance even when only a subset of the training dataset is available. So the strengths of SDRO are that it's a novel take on the group DRO technique for vision and language. It allows us to incorporate the knowledge of linguistic transformations. It is model agnostic, and we can see improvements in terms of accuracy, robustness, and calibration. SISP transformations are data augmentation tools that can be used for test time ensembling and also potentially to evaluate vision and language models. So thanks for listening, and these are the links for more details.